All right, up to this point, we've covered the fact that there are two types of architectures, behavioral and structural. We have covered both combinational logic circuits and sequential logic circuits for the behavioral architectures. Now we're going to cover structural architectures. If you remember in lab 2, you did a data path, and a data path involves usually just a structural entity of, instantiating multiple components. So a couple of definitions. What's happening here with the entity is being defined in the same file, but when you have, for example, it could just as well be mux 2 by 1 as another file here in this folder, and then called upon by the instantiations. This here, or I guess this entire portion here, is the definition of the mux. If you want to think of higher level coding, this is the function, right? When we come down to here, these are the function calls. This is the instantiation of the mux. The definition, the instantiation. And if we look here, back to what I was saying, at the lowest level, you have a behavioral architecture. Here, at the lowest level, is a behavioral architecture. We describe the behavior of the mux's circuit. When we come down to here, to our new file here, we create a mux 4 by 1 entity. Makes sense, inputs, then select. You come down to the structure. This is a structural architecture. Before we dive into it, there's two different ways of instantiating an entity. The first one is using entity work dot. Work dot basically just looks in your directory for this file. And then this second way is defining the component once again, and then you kind of get rid of the entity work dot. I highly recommend using this method instead. There's less code involved, and if you change the file, it will be able to follow it rather than having to change the file and then also change the instantiation here. On top of that, whenever you are creating a circuit, the first thing you should think when looking at a schematic is if you could make it into a structural architecture. The data path, it screams structural architecture. There's muxes and registers and adders all connected together. And then a good practice is to have U here before these mux names. So if we're looking at the structural architecture, it has 3 2 by 1 muxes, and then you have to define signals in it as interconnects. So we have mux1 out. Remember, the left side is the name of the ports of the inputs and the outputs, where these are the signals we're tying them to. Inputs 2, 3, 0, 1 are all, and output are coming from the actual port of the mux. But we still have interconnecting wires of the output from mux1 and output from mux2 going to the inputs of mux3, and we handle those with signals. Remember, signals are just wires, signals for internal connections between the muxes. So at this point, we have 3 individual entities being instantiated from the definition that we created. And these entities are all running in parallel with each other. So I created another file that shows that each of these, umux1, umux2, umux3, they're equivalent to this. Where this, I just wrote out the actual definition of the architecture and connected them that way. Now, it may seem like this is a better approach, which it may be for a 4 by 1 mux, but again, it's such a simple implementation, you don't see the real benefits of a structural architecture. Again, a structural architecture is super useful. Larger circuits, think of data path. The data path has so many moving components together. That's when the structural architecture comes in. It's for the sake of easiness. At the end, it's still VHDL and behavioral architecture happening here, right? But VHDL allows us to use these structural architectures practices so that we don't have to worry about it getting too convoluted. Imagine the data path where you couldn't do structural architecture and you had to define each process line after line. It would get hectic very quickly.